quantum physics, the world somehow is more like the grains of sand on the shore and a little bit less like the fluid, the infinitely divisible fluid of the ocean. Or so said this guy, Max Carl Ernst Ludwig von Planck, and this equation: the energy of a photon, the energy of an individual particle of light, is proportional to frequency. Energy is equal to Planck's constant h, which is a really, really small number, on the order of 10 to the negative 34th joule seconds. Energy is equal to Planck's constant times frequency. But wait a minute. Are you talking about the energy of a particle of light? I thought light was a wave. Turns out it's kind of both. Let's take a look at it with this experiment here. Here we have a light source. That's a flashlight or a light cannon shooting light, whatever light is, at this obstacle. Here we have two slits, a two-slit obstacle, and we will see the results on this screen. Ready? Let's take a look at it. Now, if light were a particle, this is what we'd expect. Imagine raindrops falling on your roof, and you have two holes in your roof. Those raindrops one drop would come through one hole, another drop would come through another hole. You'd end up with two puddles, dripping puddles in two different sections of your screen or two different sections of the floor in your house. That's what you'd expect if light were a particle. But if light is a wave, something totally different happens. If light is a wave, light hits those two slits and diffracts and spreads out and interferes and leaves you with a diffraction pattern or an interference pattern, alternating series of light and dark. So that's what we'd expect if light is a particle or light is a wave. What does light do in an experiment? And the answer is both. If we have a really strong filter that lets only one or two photons or light waves, whatever you want to call them, through per second, we'll see that those photons hit the screen one after another. Those photons hit the screen one after another, proving that light must be a particle, but they will build up a diffraction pattern, proving that light must be a wave, which is really weird. And now it's time for breakfast. I suggest toast. And the neat thing about my toaster, it's got this neat safety feature that the coils will glow red in order to alert you that the coils are hot. They put that extra light in there, that red warning light, as a safety feature. Wrong! Hot things just glow red. That's called blackbody radiation. They didn't need to make those coils glow red. You just get that coil hot enough and it glows red. That's blackbody radiation. Here is an intensity curve for that hot glowing coil. And we have light being emitted at all different wavelengths. Just a few very short wavelength waves are being emitted. Just a few very long wavelength waves are being emitted. Most waves are emitted at an intermediate wavelength. And this kind of reminds me of the speed distribution for the particles in an ideal gas. Some moving very slow, some moving very fast, most moving at an intermediate speed. Here we have a radiation spectrum, and for a hotter object, we have a different curve. Well, it's the same shape curve again. Just a very few very short wavelength waves, just a few very long wavelength waves. Most are emitted at some intermediate wavelength. But here for this blue curve, this hotter object, we see two things. Number one, that overall much more light is being emitted. And number two, the peak wavelength is shorter. And we can illustrate this with an applet here, and as you see, all we need to do is change the temperature of the star or the oven or whatever is emitting the radiation, and we will change the amount of radiation and the color, the overall color of that radiation. So again, there's the toaster emitting some long wavelength visible light, some red light. The filament of an old-fashioned hot incandescent light bulb is hotter. It emits more light overall and more light at shorter wavelengths. It glows white. And then there's you. You are not as hot as a toaster. It would be cool if you could make toast with your hands, but you do have a temperature, and because you do, you emit infrared waves. Even in a totally dark room, you emit your own light. Not light that you can detect with your own eyes, but light that you can detect with night vision goggles. Infrared waves. Blackbody radiation. Nice looking curves there. And Max Planck figured out an equation for those curves, and he did this with two revolutionary concepts. Number one, the energy of a light wave is proportional to its frequency, and number two, that energy is quantized, meaning the frequencies are quantized, meaning that not every frequency light wave will show up. This is something we've seen before, standing waves. We can have that standing wave or that standing wave or that standing wave as n goes from 1 to 2 to 3. But we've seen this before on this string. Only certain frequencies will give you these standing waves. This is how instruments work. Some instruments anyway, lots of different waves, but only some of them resonate, and those are the ones you hear. Those are the ones that show up. Those are the light waves. Let's take a metal surface and shine a light on it. No, we're not talking about reflection here. We're talking about the interaction between light waves and electrons in that metal, and there's not much to talk about with this long wavelength, low frequency red light. It doesn't do much. This green light, however, a little bit higher frequency, it does do something. And by do something, I mean it ejects an electron. Shine this green light on that metal, and an electron will get excited and jump off, but not that excited. This electron will be a somewhat lethargic electron, not a lot of energy. And yes, we will have a picture of a lethargic electron in just a couple minutes here, but we have bluer light now. Shorter wavelength, higher frequency blue light ejects a more excited, faster moving electron. This is known as the photoelectric effect, and it is surprising. Surprising because that red light won't emit any electron, even if there's a whole ton of it. If light is just a wave, then you'd figure that if you pump enough red light, you gotta do something. But no matter how much red light you pump on that metal sheet, no electrons will be emitted. There must be something quantum. Something quantum about the interaction between light and electron, and that again is the photoelectric effect. And here's an applet that shows it. Here we have a light source. It's shining on a piece of metal there. We can adjust both the intensity of the light source and the wavelength, the frequency or wavelength of the light. They're connected, of course. And then if we eject an electron, we can control it with this battery which is hooked up to a capacitor. We can control those electrons. We can stop those electrons with an electric field. So let's do it. And we're starting with this red light, this low frequency light, and it's not ejecting any electrons, so we can change the frequency of the light, make it higher frequency, shorter wavelength, higher frequency light, and some electrons are being ejected here. We can adjust the voltage there. We can figure out just how much of an electric field we need to stop those electrons and get the current back to zero. We can write this equation, which is a complicated looking equation. It's just a conservation of energy equation, and this is what won Einstein his Nobel Prize for, again, the photoelectric effect, trying to understand the big mystery. Why won't red light, no matter how much of it there is, why won't red light eject electrons from a metal? Anyway, you'll recognize the center term, 1/2 mv squared. That's the kinetic energy of the electron. This is an energy equation. What about the left? This involves the stopping voltage, the voltage we need between those plates of the parallel plate capacitor in order to stop the electron. Voltage is equal to energy per charge, so you multiply voltage by the charge of the electron, and that's the energy needed to stop the electron. Over on the right, what do we have there? That's Planck's formula for the energy of the photon. And phi, that's the work function, the energy needed to free the electron from the metal. So that's the deal. That's the quantum reality. Light is not really acting like a wave here. Light is acting like a particle. Light comes in with a certain amount of money, a certain amount of energy. And the question is, do you have enough energy here, Mr. Lightwave, to bail that electron out of jail, to pay the work function needed to get that electron to get out of the metal? And if you do, then you do, and the electron is free, and you can give the extra energy to the electron. It shows up as kinetic energy, but if HF is less than phi, you're not being ejected from that metal, no matter how much of it you have. Oh, and by the way, this equation here, this gives you enough information to calculate Planck's constant, that really small value for Planck's constant. And that, again, won Einstein his Nobel Prize, but I don't have a picture of Einstein. I figure you know what he looks like. Here's another guy, though. Here is Louis de Broglie. And I am totally jealous of Louis de Broglie because he got his doctorate in physics and even a Nobel Prize for doing, well, here's what he did. He took E equals PC. That's a classical physics equation for the energy of a light wave. Again, energy is equal to momentum times the speed of light. Not something we talk too much about anymore, but anyway, there's a well-known equation. And he took the brand new Max Planck equation for the energy of a light photon, and you know what he did? He put them together. Okay, so far so good. So the momentum of the light wave times the speed of light is equal to Planck's constant times the frequency of the light wave. And now another fairly straightforward equation. Velocity is equal to frequency times wavelength. We've seen that, so plug that in for C. and then rearrange. Cancel out frequency, and you'll get an equation for a lambda, and you can name it after yourself. The de Broglie wavelength. I know it looks like de Broglie. The de Broglie wavelength is equal to Planck's tiny constant divided by the momentum of the what? Of the light wave, or de Broglie said of the anything. And that is, I guess, why he deserved the Nobel Prize. Anyway, could you ever measure this wavelength? Well, again, h, that's a tiny constant, 10 to the negative 34 joule seconds. So the wavelength depends on h, but it also depends on momentum. Talking here about we need a tiny momentum in order to get a wavelength that could be measured. Well, what could have a tiny momentum? You'd want a tiny mass and a tiny velocity. I know, you saw it a second ago. How about some of those slow-moving electrons, those lethargic electrons? You see the path that we're making here. Max Planck said that light could be quantized. Einstein showed that quantization involves the interaction between light and electrons, and now de Broglie is showing that electrons themselves act as waves, which means they diffract. If you take a wave, and we saw this earlier, you take a wave and you shine it at two slits, for example, it'll give you a diffraction pattern. Light spots, high intensity, where the waves add up in phase. That's geometry. When wavelength is equal to the distance between the slits times sine theta, that theta is a maximum. And that's what happened when Davison and Germer, back in the 1920s, less than just a couple years after de Broglie published his thesis here, his dissertation, fired slow electrons at a piece of metal and detected those scattered electrons. It's the same sort of thing. We're not using a barrier with slits in it this time. We're using an even smaller d, the distance between atoms in this crystal lattice. But anyway, you got those electrons coming in, those electrons reflecting out. You have some geometry there, and when lambda equals d sine theta, you get a maximum, you get a bright spot, you get evidence that electrons act like waves. Again, this is crazy. This is what we saw earlier, but we're not talking about individual light particles now, or photons. We're talking about electrons, matter, mass, going from the source through the slits and onto the screen, and showing that matter is a wave. So here's an electron just free in space and having a great day. But what if you put that electron in a box? Well, again, if the electron is a wave, then some of those waves will show up in the box. And you don't really want to put an electron in a box, but you do want to put them in atoms, and atoms are containers for electrons, you could say. Anyway, we have some wavelengths, some frequencies show up, and that means some energies show up. So what we have here is quantized electron energy levels. We went from light having quantized energy states, and now we're talking about electrons having quantized energy states. And if the electron goes from a higher energy state to a lower energy state, it's going to emit a photon, and that photon will have a certain amount of energy, and then you can calculate its frequency and its wavelength and get discrete spectral lines. Discrete spectral lines like these. This is the spectrum of a fluorescent light bulb. Discrete lines corresponding to individual frequencies, corresponding to individual energy transitions for the electrons in the gas inside the fluorescent light bulb. Anyway, it's discrete, it's quantized, it's different than the spectrum from the sun or from an old-fashioned hot incandescent light bulb, which gives you a continuous spectrum, which gives you a rainbow, which is something we've talked about before. And again, we're seeing totally new things pop up with modern physics, but also connections to things we've talked about before, connections all the way back to the most fundamental thing you can talk about in physics, and that is measurement. And this is Werner Heisenberg and his famous uncertainty principle. He states, and he proved, he showed that there is a limit to the maximum possible precision for any measurement. In other words, you cannot, for example, know the exact position, delta x equals 0, and the exact momentum, delta p equals 0. You cannot know simultaneously the exact position and momentum of a particle. The uncertainty in those simultaneous measurements will be greater than h bar over 2. H bar being related to Planck's constant, which shows up everywhere, of course, everywhere in modern physics. So what we're saying here is that Heisenberg took the de Broglie wavelength seriously. He said if matter really is waves, that's okay, but not all waves are created equally. Here's the example of a wave. This wave will give you good position data. It's pretty clear where that wave is, but how would you measure the wavelength or the frequency or the momentum of that wave? Here's another wave. This wave looks different. This wave gives you a more meaningful value for the wavelength or the frequency or the momentum. That's good, but where is the position of that wave? Delta x is bigger, delta p is smaller, or delta p is smaller and delta x is bigger. What are you going to do? Well, who are you anyway? We're talking to this electron after participating in our diffraction experiment, and we find the electron here on the screen, and we say, hey, how you doing? Can you tell me a little bit about yourself? For example, which slit did you go through? Did you go through the slit on the left or the slit on the right? And the electron just looks at you and says, well, kind of really a matter wave. I don't really, do that one slit or the other thing. And you look at it, well, you had to have gone through one slit or the other. And the electron said, well, if I went through one slit or the other, I'd be a particle. I went through both and diffracted with myself, because that makes sense. Then you scratch your head and you say, now listen, how could you have gone through both slits? And the electron says, well, don't you know anything about waves? I mean, how did I make a diffraction pattern if I'm not a wave? So did he go through one slit or the other? And that leads us to something I don't want to talk about. I don't want to talk about Schrodinger's cat.